Welcome to Mancinelli's Math Lab. Here's the mug I usually use when doing math. Just seems proper. So, anyways, something different today. I'm going to cover a topic and example related to real analysis slash advanced calculus. So, here is just the setup. I want to first write down the definition I'll be using for pointwise convergence. So I have a sequence of functions, and I'll usually omit the x. X is a member of E. I have a set E. A lot of times, in an abstract sense, we call that a metric space. Then we can talk about this concept. N is going from 1 to infinity, so natural numbers. We have a sequence, and the sequence happens to be each member of this family happens to be a function. So, we want to talk about pointwise convergence. So the first thing I want to do is write down the definition of a sequence of functions converging pointwise. So, definition. Okay. We have that the sequence, so the sequence Fn, okay, and I'm omitting the details. N goes from 1 to infinity, and it's a function of x, where x is a member of E. So the sequence converges pointwise on E to F to a function, say F, if for each x in E and epsilon greater than 0, okay, there exists, or there is, n, capital N, natural number, okay, capital N, we're choosing this to be a natural number, and I'll go over what this stuff means in a second. There is an n such that, let me just write it out. I'm not going to abbreviate everything. I can write everything in symbols if I want, but I'll write it out. So such that if little n is greater than or equal to capital N, we have the following situation. Then the distance, and this is how you want to think about this. You want to think about this as the distance between the sequence, the members of the sequence, and the limiting function, the function which it allegedly converges to, is less than epsilon. Now let me just first write down a few things about this. Okay, so this is the definition of pointwise convergence. And as I mentioned, E could just be a metric space, although for the example I'll cover, it's just going to be the real numbers actually. It may also be a subset of the real numbers. So, what's going on here? Well, a couple of things you need to realize here. N is what you have control over. N is what you want to find in a problem like this, okay? And in this case, for a sequence of functions which converges pointwise, oftentimes we write the following. We say that N equals kind of, well, it depends on x and epsilon. N depends on x and epsilon. This is the sort of distinguishing feature. So N depends on x and epsilon. So the idea here for pointwise convergence is that I fix an x, I fix an epsilon, and from that, once I've established those, once I just choose those, once I just let x be a member of E, let epsilon be greater than 0, then I have a choice. I get to do some sort of probably algebra to figure out a value of n, such that when I pick this value of n, this capital N, it's a natural number, anytime I take members of my sequence of functions, okay, where the index is greater than that n, the distance between the members of my sequence and its limiting value is small, is very small. We're choosing epsilon to be arbitrary. We want this distance to be small. In other words, if epsilon is arbitrary, this might as well be 0. These get arbitrarily close, they converge. Okay, so one other thing I want to point out here is that it's important to remember that we only need this distance to be small for an infinite number of values of little n. In other words, this doesn't have to be very small for any finite number of terms. I mean, this capital N could be like 100. There's still going to be an infinite number of terms of little n that exceed 100, because this little n is going to infinity. I hope you see what I'm trying to say here. All right. Let's write down the definition of uniform convergence. I'm only going to change a few things, and I'm doing it this way so hopefully you see the distinguishing feature. So again, n, our choice of capital N, depends on x and epsilon. Let's get rid of this. And now I just want to change something slightly. I'm going to get rid of this. So all I have now is that if for each epsilon greater than 0, this is uniform. Change this to uniformly. On E. Now I will put for all x here. For all x in E. And hopefully you're familiar with this notation. This means for all x that is a member of my underlying metric space E. So the sequence converges uniformly on E to a function f if for every epsilon, so I'm still choosing an arbitrary epsilon, usually a small number, there is a natural number n such that if my indices, okay, my terms of my sequence of functions, if those, the little n, exceeds capital N, if I go far out enough in my sequence, the distance between the sequence of functions and the limiting function is small. Then I put for all x in E after that. So what I'm saying here is that when we make the choice of capital N, n will, in this case, will only depend on epsilon. It does not depend on x at all. So n depends only on epsilon. And this basically means that I can let x vary, and it should not change the condition, the fact that f, the sequence of functions, fn, should converge to f. So hopefully you're seeing that uniform convergence definitely implies pointwise convergence, but the converse is definitely not true. Now, let's look at an example, since I think this is probably still confusing. Real analysis, in my opinion, is one of the toughest subjects in math. So let's look at an example. Hopefully we can make sense of this. Okay? I'm going to look at a fairly straightforward example, mostly because I just want to get the point across. Here is the situation. I want to determine if the sequence of functions, let's just say fn equals x over n, converges pointwise, uniform, let's just say pointwise or uniform, or uniformly on r. Okay, real numbers. So does this sequence of functions, do they converge pointwise or uniformly on the metric space R? So this was playing the role of what was previously called E, okay? And, well, how do you approach something like this? I want to use the definition I wrote down. Now the thing you should do, and people have trouble with the logic here, but what you should do here is you should first start with some scratch work. Some scratch. I'm not just going to jump right into the proof, because remember what we need to do. We need to find capital N. Okay, so what do we want? We want capital N in N. This is what we have control over, is the natural number N, such that if little n exceeds capital N, then x over n, the distance between x over n and the limiting function, which I don't know, is less than epsilon. So we need to find this. We need to find this. Find n. That's always the situation. And also right now we need to figure out what f is. Now to figure out what f is, we can just use a limit. Just use basically Calc 1 business to figure out what the limit is as n goes to infinity. So I'll just say here now, notice that the limit as n tends to infinity, and again I should probably write this, I'm fixing an x. If I fix an x, notice for x and r, just pick an x that's a real number. We have that the limit as n tends to infinity of x over n is equal to 0. This is pretty clear. Now again, it's important to realize that I'm first fixing an x and then I'm taking the limit. Okay, so in other words, I'm looking at pointwise convergence because I'm picking an arbitrary x and then I want to see what the sequence of functions converges to. So this is not at all the proper way to show this when you get to a real analysis course. We need to use the capital N and epsilon. We use the epsilon definition. So we do know though that this will be playing the role of our f. This is our f. That's our limiting function. So now, let me come back up here. Okay, let me just say this. So hence we want we do want the following then. We want that x over n, this is still my scratch work, minus 0 is less than epsilon if n is greater than or equal to n. And we still need to find capital N, right? We need to find this capital N right here. So what we're going to do is the following. And by the way, what does this simplify to? This says that I have the absolute value of x over n is less than epsilon, right? Because little n is a natural number. We don't need absolute value there. X is a real number. It could be negative, could be 0, could be positive. And by the way, if it's 0, I mean, obviously, it's going to equal 0. Let's continue with our scratch work, because remember, it all comes down to finding this capital N. It will absolutely depend on x, and it will absolutely depend on our choice of epsilon. So, pointwise convergence is what we're looking at. Now, let's see what we can do. So I'm going to start with what we want. It's kind of backwards when you approach a problem like this. It's almost like cheating. So we want, I'll just write it out one more time, Fn minus f less than epsilon. Equivalently, for our situation here, this says that the absolute value of x over n is less than epsilon, right? That's what we want. So, when, or just for little n bigger than the natural number, capital N. Let's do some manipulation with this. Do some algebra. Let's take the reciprocal of both sides, and let's multiply both sides by the absolute value of x. So this is equivalent to saying 1 over little n is less than or equal to 1 over capital N. Remember that when you take the reciprocal of both sides, you need to switch the inequality. All right. Now let's multiply top and bottom. Well, let's multiply both sides by absolute value of x. So absolute value of x over n is less than or equal to absolute value of x over n. We want this to be less than epsilon. We want absolute value of x over little n to be less than epsilon, but I don't have control over little n. Little n is going to be tending to infinity. I do have control over capital N. So if I want this is why it's almost like cheating, is I want this to be less than epsilon. This is what I want. So I'm going to work with that now. So when is this true? So then absolute value of x over n is less than epsilon if, just do some algebra here, multiply both sides by capital N and divide by little epsilon, if absolute value of x over epsilon is greater than n. This is our choice of n. This is how we'll pick n. So this is how we will choose n. Remember that this is what we have control over. In these problems, capital N is what you actually need to find. Finding the correct n is what will actually prove the result. So now, think about this for a second. What we're going to do is we're going to say the following. This is why people get so confused. Is I'm going to say, look, pick n greater than absolute value of x over epsilon. So notice, n depends on x and epsilon, pointwise convergence. Okay? If I choose it this way, based off what I've just done, that means epsilon, right, this quotient is less than epsilon, but as long as little n exceeds capital N, then absolute value of x over little n is less than absolute value of x over capital N, which is less than epsilon, which means we're done. I know it's confusing, but write it out. I hope this makes sense. Now I'm ready to write the proof. I'm really going to just write down the proof. This is my scratch work. Okay? So the proof of pointwise convergence is as follows. Okay, so proof pointwise. Just going to prove pointwise, and then we'll talk about uniform. So let's pick n, a natural number, such that n is greater than absolute value x over epsilon. So n could be huge, right? N could be enormous. In fact, if epsilon is very small, n could be very large. But it doesn't matter. Because it can be not true for a finite number of values. It doesn't matter how big n is. If n is 1,000,000, then little n, as long as it exceeds 1,000,000, and little n is going to infinity, it's still going to be an infinite number of values of little n such that it's true. So this is how I'm picking n. And I'll just say over here also, note that right here, n depends on x and epsilon, right? So if I pick n this way, then if little n exceeds that capital N that I've chosen, we have the following. We have that the distance between the sequence of functions and the limiting function, which I called f, is equal to, okay, well, my sequence of functions is x over n, and we know, well, we saw using just limits that it should approach 0. And just doing some straightforward algebra here, this is absolute value of x over n. This is less than absolute value x over capital N, which is less than epsilon. And we're done. I mean, this proves it. So pointwise convergence is taken care of. I hope this makes sense. You need to do the scratch work beforehand so that you can choose the correct value of n. Now, let's look at uniform convergence. And do you think it converges uniformly? Well, you remember, it converges uniformly if I can pick an n, a capital N, which does not depend on x whatsoever. I claim that it does not. I claim that this sequence of functions does not converge uniformly. On R. Okay, I claim that it does not. So here's what we can do. I need to be a little careful with the logic here again. To show that it does not converge uniformly, we need to pick, we need to find an x, actually, and it can be variable. So we're not fixing an x, okay, but we can pick an x such that the convergence doesn't hold. So what we're going to do, and also we need to, I guess, find an epsilon as well. So go through the contrary to the statement for uniform convergence. I want to show that it's not uniformly convergent. So what does it mean for something to be not uniformly convergent? Okay, we're going to let epsilon be less than 1, and we can pick x equals n. This is pretty clear, I think, what happens here. F sub n of x with x as n is equal to 1. Right? So in other words, what I'm saying here is I have the following. Fn of n is equal to 1. Right? If I choose x to be little n, then it equals 1. Alright. We have that the absolute value of Fn of n minus 0 is equal to 1, which is greater than epsilon. So for this choice of x, I cannot find a capital N. So thus, there is no n. There is no capital N natural number such that Fn minus f is less than epsilon for x equals n. Hopefully this makes sense. If I choose this particular value of x, I cannot get the sequence of functions close to, in this case, 0. So it does not converge uniformly. Alright, that takes care of it. Hope this was helpful, specifically for the individual who asked me this question. And tell me what you think.